So let's just start. So aloha and good evening, everyone. Thank you so much for being here this Wednesday evening. Quick introduction about myself. I am Vinod Vidu, moderator of this panel session. I work as a Director of Strategic Initiatives with Oceanit. Today, we have an amazing panel on global energy transformation, decarbonizing the world's energy system, where we'll try to explore different sides of the energy transformation efforts that's occurring around all of us. Quick background on the panel theme. As we all know, the climate change costs and impacts are driving a mandate for energy transformation away from the energy sources, as we know, the fossil energy that creates climate impacts towards a greener energy. Less climate impactful energy. Principally, these are, as we all clearly know, are driven by solar, wind, geothermal, or other non-fossil fuel sources. At the same time, we all understand that this industries, the energy industries as a whole, is pretty complicated and massive. Transforming is not only a technical issue, it's a major geopolitical challenge that sort of encompasses everything that is in the what we call TCOP, technical, economical, commercial, organizational, and political. So to make things matter worse, the massive installed infrastructure that is already in place that enables the world to operate on fossil energy has similar legacy and ownership issues, including the major energy supply chains, the upstream exploration, production, transmission, refining, and distribution, everything included. So when we look for change, all of this must change or adapt for the world to transform from fossil to non-fossil sources of energy, including, then that's where the challenge comes in, I think, including government policies, national energy companies, and international energy companies to the new world order. So how do we accommodate these massive forces to enable science, engineering, and technology to intercede and save our planet? So to discuss and explore some direction or to build on their expertise, we have three great panelists today with decades of experience in policy, major global industry operations, and decarbonization initiatives. So to give you a structure for the panel, so here's the format that you should expect. Each of the panelists will first share their high-level thoughts and remarks. I think each of the panelists will be roughly take 10 minutes. After that, I would like to ask the panelists a couple of questions as panel questions, and we'll open up for panel discussion and eventually open for public questions. So as first step, let me introduce Elena Melkert. Elena Melkert is a 36 years of experience veteran of the energy industry, recently retiring as Director, Upstream Oil and Gas Research Division at the U.S. Department of Energy. Her over 3 decades of experience at U.S. DOE includes managing a range of energy programs, including numerous policy, technology, and research partnerships with industry, academia, federal and state agencies, and NGOs. So with that introduction, I hand over to Elena. Please go ahead.
I am Elena Melkert, and I've actually been in the oil business for 40 years. I served 36 of those years with the Department of Energy. I worked in the oil fields operations, field operations for 8 years, both in the private sector and for the Department of Energy at a giant oil field outside of Bakersfield that was owned by the government. Another policy, technology, interface type of situation. It was a commercial oil field that the government owned in partnership with Chevron. And I was a production engineer and then a reservoir engineer before I came to Washington to manage that oil field, as well as then go into the research program. But my whole career has been, most of my career has been at that policy technology interface. So let me go ahead and launch these slides. So Vinod asked me to talk about my experience and the fact that I've served 7 presidents here in Washington, D.C. in my career for the Department of Energy. And so he asked me to talk about some of the, the lessons learned associated with what I've seen over the course of this time. And so what I've learned is that change is defined by the starting point, that it takes time and other resources, especially money, that you need tools, and that there's a process for ensuring the change that you want. So to put a finer point on this energy policy goal, I want to turn to the Energy Information Administration. EIA is an independent federal agency of the Department of Energy, and each January, EIA publishes the annual energy outlook that forecasts future energy supply and demand. Obviously, the Energy Information Administration published this year's annual energy outlook before inauguration. So let me point out that EIA models current policies in place, and so it's policy neutral. And the oil price used in this analysis was $95 per barrel in 2050. So the next 5 slides are taken from the 2021 AEO, which forecasts energy supply and demand out to 2050. And this period coincides with the president's energy policy goals. So I'd like to quickly make a few points about each. So this slide shows energy demand with actual data for up to 2020, and then forecasted numbers up to 2050. The model forecasts that US consumers will use more energy going forward than ever before, mostly for power generation and in the industrial sector. This slide shows that even though energy demand is increasing, we are using that energy more efficiently. So this curve is going down to 2050. So here is a forecast regarding consumption by fuel, and the consumption profile is probably pretty familiar. It's comparable to what we have now with oil and gas dominating the consumption, but you'll note the dramatic increase in consumption of renewable energy. This slide shows that oil will be used primarily for transportation and by the industrial sector. In the industrial sector, oil and gas are both used as a fuel and as a feedstock. And that natural gas is used primarily for power generation. I just realized that this is the wrong slide. Okay, so normally this, if my correction had been complete, this graphic over here would show natural gas, not petroleum. And it would show that natural gas was used primarily for power generation. Okay, this slide shows that US production of oil and gas will continue, making it possible for the US to possibly continue exporting oil and gas. So that's what I call the starting point. You've got to know where you are and contrast to where you want to be. So looking at some insights about change, change takes time, you need tools, and it's a process. So I'd like to move into comments about that a little bit.
Okay, well, what I was going to talk about here a little bit is sort of beyond net zero, and talk a little bit about how Hawaii might show the world really a good example of not just how we can lead in the energy transition, in net zero transition, but in sustainability as a whole. So first, a little bit of context setting. As it is now, fossil fuels remain the primary source of energy in the world. About roughly 84% comes from the combination of oil, gas, and coal, as you can see in this plot here, with the rest made up by nuclear, about 4%, and then the rest from renewables, including hydropower, wind, and all that. So in order to wean off of fossil fuels altogether, it will take quite a while. There's a lot of energy, to use the term, that is being put into actually weaning off from fossil fuels. And that, there's no doubt that will eventually happen, but it will take, in most scenarios and most opinions, decades, and will take also significant investment, and not without some pain. Again, to put things in perspective, in 2000, the percentage of the energy coming from fossil fuels was 86%. So actually, the change from the last 20 some years is a mere 2%, despite all the investments in wind and solar in particular. But also put things in context, the energy industry as a whole, and if you really include the actual energy use in the industry, as well as used in transport, as well as the use in buildings. If you aggregate all that and also include combustion, fugitive emissions, and all of that, then it's arguably responsible for about 3/4 of the emissions. So the energy sector as a whole and its aggregate usage downstream of it is indeed responsible for major part of the emissions. So that has to be addressed. If we look forward to the future then, and we'll talk a little bit what future are we talking about here, what kind of time frame, there is no doubt that electricity demand will rise overall in almost any scenario that you can imagine. And it's very logical to expect that a lot of that will be provided by photovoltaic and wind. For example, already as of 2021, in just the last decade alone, the cost of photovoltaic has already fallen by more than 70%, and quite similar numbers to wind as well over that same time frame. So if we fast forward, it is very feasible to expect it to fall further. And hence, by 2025, we expect photovoltaic and wind to become competitive with natural gas power generation in most parts of the world. And in most scenarios out there, the overall, I think Elena already pointed out to a few, the overall demand for energy would increase. In some of them, it would stabilize or maybe slightly fall back. But in general, if you expect that the world will continue to lift people out of poverty and to demand more electricity for connectivity or what have you, the overall demand for energy would increase with time. However, there's still about 1/3 of the world's inhabitants that still does not have access to electricity today. So there's a great part of the world that still has to be electrified, if that is a feasible route to get energy to them. Now, with all the scenarios out there, there's really no credible scenario out there in which hydrocarbons disappear completely by mid-century. There's a lot of commitments made by countries, made by companies, by corporations, to go to net zero by mid of the century. However, there's really no credible scenario in which the hydrocarbons will disappear altogether. It's just not feasible. So they will remain important in just about any scenario out there as the world adapts to support that net zero future. And just to add some detail to that, I show here some scenarios which were developed by Shell, published in February of this year as part of the Shell Strategy Day. So this is publicly available data. And in it, they talk about 3 scenarios, 3 sort of bookend type scenarios, which they call waves, islands, and sky scenario. Essentially, the sky scenario is an accelerated scenario which prioritizes health and the environment over all else. The wealth first scenario is late but fast, and then somewhere in between is a security first scenario, which also balances the two, and it's you achieve 2.5 C. So it's a late but slow, so sort of in between. And if you look then in the sky scenario, which is really the most aggressive of the lot, you can see out to 2100, there is a significant electricity consumption growth, predominantly coming from renewables. That's shown in the light yellow here, the navy blue, and that replaces, the darker blue, which is essentially fossil fuel generation of electricity, so that almost diminishes. And then on the reddish colors, you've got liquid fuels, because the world will still need, of course, liquid fuels for a variety of chemicals and other hard to electrify sectors. And those also will start to become predominantly non-fossil fuel based. And then you've got the gaseous fuels, which was also shift from fossil to non-fossil. However, fossil fuels don't disappear altogether, even out to 2100. Maybe to add a little bit more color to this scenarios, you can see here, the 1.5 C scenario, which is a sky scenario, which is where we aspire to be, and then you've got the waves in between, and the 2.5 C, which is insufficient to reach the Paris goals. And then plotted on this here, a lot of things have to come together. So net zero CO2 emissions have to be reached, but also at the same time, electrification of vehicles has to reach very substantial fractions. Now remember, maybe in 10-20 years, all new vehicles will be electric, but you still got a large fleet that is existing, which has to be incrementally replaced or decommissioned. And then electrification has to penetrate other sectors of the economy. Deforestation has to come in and play its part, and so on and so forth. So if you really look at all those scenarios, we need all of those solutions to play their part. You name it, hydrogen and so on. But even then, if you look carefully here, and basically the whitish part is somewhere between 2100 and beyond. That's the light colored here. Even then, oil use would fall below 1970 levels, and Elena already talked about that. So even out there, in most scenarios, we still need fossil fuels for a long time to come. So how, I thought it would be interesting to talk about how an integrated energy company such as Shell, and Shell and most of the European majors are quite progressive in their approach to net zero, both in terms of commitment, but also in terms of reimagining their business. How might then their business models change? Because ultimately, if you want to stay relevant in that world, you have to rethink what it is that you provide. So you can see again from the Shell Strategy Day how the critical business drivers factor in the different pillars that they build. So for example, for Shell, they defined a growth pillar, which is essentially the future of energy as far as they're concerned, a transition pillar, which enables that, and then an upstream pillar, which essentially bankrolls or finances that. So this is kind of your existing business, and this is kind of your future business. And if you look, it's a transition. It's basically a smooth transition from one to the other, because you cannot afford to completely cut off, for example, the upstream pillar, which is going to bankroll the growth pillar. Otherwise, you won't have either. You won't have the existing energy supply and will not have the ability to actually grow in the first place. And we will talk about this later, maybe in the Q&A, but importantly, it's business models and customer-facing solutions become really important in that realm. So it's not just about doing business as usual, but actually the way you conduct the business and deliver that business becomes really different. And I'll just leave you with that thought, and with the fact that in order to achieve net zero, the solutions must be broad, they must be deep, and they must be multi-pronged. There's no way to do it all with electrification, for example. So net zero transition doesn't equal electrification. It's enabled a lot by electrification, but they're not, not just electrification. You need also natural sinks. Carbon capture and sequestration is a big deal. I think we'll hear about that later. Electric mobility is a big part of it, biofuels, and of course, renewable power, but also operational efficiency in the existing asset base is critical too. And that, all together, that might get us close to the aspired net zero transition.
For the opportunity to talk about a topic I've worked on for quite a while now. Carbon capture and storage is a topic that's been around for quite some time. It's been researched for over 2 decades, but it's obviously seeing a resurgence of interest now, and we can talk a little bit about that in the course of our discussion here. I thought I'd go through a little bit of the basics and then deviate a little toward the end and show you some things that might help you understand what we're really trying to do in the subsurface when we're talking about storing CO2. So very similar to the last slide that Hani was just showing, actually, is a different way of looking at the same information, which is essentially thinking about where we are going to get large-scale emission reductions going out into the future. And so this is one version of that kind of information that was seen earlier. And it also sort of hints at what areas might be playing different roles in that reduction. So if the black line is sort of what we've been doing up until now, and then point forward, we're thinking about these different wedges that can be used to reduce emissions through time to ultimately achieve that reduction that's on that light blue curve there going forward at kind of hugging the bottom of those colors. So you'll see that there's about, a third of that reduction coming from efficiency of different processes that are out there, maybe another third coming from renewable energy. And then the final third would be coming from a mixture of things like carbon capture and storage, which I work on, or switching fuels, say from coal to natural gas, or from natural gas to renewables, et cetera. So the important point for me in this discussion is that none of these is meant to solve the entire problem. It has to be a mixture, as you were just hearing. And so it's normal to think of carbon capture and storage as representing maybe 10 or 15% of the total emissions reductions we can expect going forward. So it's not meant to be a permanent solution. It's meant to be a bridge into a different future, say by 2050. And the point is that every molecule of CO2 that gets emitted today stays in the atmosphere for something like 200 years. So anything we can do to reduce that number of molecules that are entering the atmosphere today is a great benefit going forward. So that's really the aim of carbon capture and storage, is to reduce those industrial emissions that exist today and to address any of the new ones that may come forward in the future. So if you're not familiar with it, carbon capture and storage, sometimes referred to as carbon capture utilization and storage, is a rapidly evolving business, but it really is populated by 4 main sectors, and those are shown in the diagram towards the bottom. So you have different sources of CO2 emissions that are out there. These could be electric utilities, these could be natural gas processing facilities, they could be cement, steel, basically anything that's requiring power and or using different types of natural resources ends up emitting some CO2 in the process. So these are emissions that are quantified and reported to the U.S. EPA, and so we have a very good idea of what the profile of these emissions look like through time. Currently, there's no there's no legislation to cap the amount of emissions. So we have other incentives for trying to reduce these emissions that we can talk about at the end. But essentially in that second image, you see that there's got to be some kind of capture equipment installed. So you need to actually install some new bit of engineering to capture the emission streams that's coming off of those different sources. And so not all CO2 emissions are created equal, and so some emissions are cheaper to capture than others. But we have very good technologies for capturing emissions from most of our most common emission sources. The cheapest would be, say, the emissions coming off of, say, an ethanol plant where you're converting corn into ethanol. And then from there, you might be moving into natural gas processing and further up into hydrogen production. And then lastly, the hardest things to decarbonize would be the production of cement and steel. So those two industries actually almost require CCS to decarbonize in order to contribute to low carbon goals. And in the case of capture, you transport the CO2. In this case, you're usually compressing it and moving it by pipeline. That's the most efficient way to move it. There are now ships being designed to move CO2 in the marine environment, and that is a rapidly evolving field as the CO2 starts to become more of a globally traded and shipped product. And then lastly there you see the CO2 sink, which is essentially the part that I work the most on, which is what do you do when you actually need to get rid of the CO2? We don't want it in the atmosphere, so we'd like to stick it into the deep subsurface geologic environments. And in a lot of ways, this is really a natural way to think about it, because a lot of the carbon that is produced in carbon dioxide is actually carbon that was coming out of the earth in some form of hydrocarbon originally. So returning it to the subsurface is a natural way to think about it. In some cases, you can use the CO2 in the utilization component to enhance oil recovery if that's part of an economic plan. But in the majority of the cases, the volume of CO2 and mass of CO2 that we're thinking about is actually needs to be injected into what we call saline formations. And these are rock bodies in the subsurface that basically contain pore water that is more saline than say ocean water. And if you're having a hard time imagining how you get CO2 to go into rocks, the first thing to imagine is that we got the oil and gas out of the rocks in the first place. So there is space in the rocks by which we refer to it as porosity, and we can actually push the CO2 back into the rocks the same way we've produced hydrocarbons out. And the obvious way to think about that is just your sponge. You can actually put water into your sponge even though it looks nominally like a solid. Okay, so one thing to point out is that globally this topic is actually ramping up quite fast, and in the North Sea part of Europe and the EU, we see a lot of active projects developing. Most of these are taking advantage of offshore storage, where the CO2 is being transported into the offshore environment, where it's then injected deep into the subsurface. And by deep, I mean at least a mile or say 1,500 meters beneath the seafloor. So deep into the subsurface, not the sediments or the water column. And here you're just seeing different paths of potential transport of CO2 from the emission sources to the most likely emission sinks where you would actually be storing the CO2. So we know that Norway has been doing this since 1996 in the North Sea, where they've been capturing CO2 from a gas processing facility and re-injecting it successfully in the North Sea. And they have a second project in the northern part of the country that's also working along, and now we know that there are projects being developed in the Netherlands as well as in the UK. So this is active developments in that part of the world. I was lucky enough to be able to go over and work on a project where they're actively injecting CO2 offshore off the energy port in the North Island of Hokkaido. So this is a project where they were essentially testing their ability to capture emissions from a gas processing facility and then inject that CO2 using a well that actually has a surface location essentially on the beach there at that red dot. But the bottom hole location is actually in the offshore environment in the deep subsurface. So it's a long deviated well to reach the injection point. And so we were able to go over and use some technology that DOE had funded us to work on to monitor the injection site to make sure that the CO2 was staying in the intended injection interval. And the project was highly successful and is now concluded. In the United States, if you think about emissions, the inset map in the upper left kind of shows sort of where most of our emissions are in the United States. They're dominantly in the upper Midwest and the Ohio River Valley, and then along the Gulf Coast. And the emissions in the upper Midwest are largely related to either ethanol production or power production. Not entirely, but dominantly. And then in the Gulf Coast, we see a lot of emissions related to a diverse industrial processes. Everything that is in your kitchen is probably derived from something that was produced in one of these places. So we think a lot about these emissions and how we might be able to basically address these historic emissions to ongoing emissions, I should call them, to reduce them so that they're not emitted to the atmosphere.